Hello everyone. Today let's solve the problem number 153. Right. So here this one I'm speaking of find minimum in rotated sorted array. Right. Find minimum in rotated sorted array. So here let's see what the question states. So we have given a sorted array that is rotated k times. So here you can clearly see. Let's come to the first example. Just give me a second here. So yeah, we have been given a sorted array. So basically this was the array 1, 2, 3, 4, 5. Right. So this is sorted thrice, three times basically. So this is sorted three times. So here it will come 5 will be in this spot and 4 will be in this spot and this one 3 will be in this spot. Right. So now it will be 3. So basically 3, 4, 5, 1 and 2. So we have been given sorted array sorted which is rotated k times. Sorry, we have to find the minimum element and big O of logarithmic n times. They have strictly mentioned that we have to find the minimum value in the sorted array that is rotated this one k times. We have to write the algorithm in big O of logarithmic n time. Right, so we have to write the algorithm to find the minimum element n big of logarithmic n times. Right, so the array contains unique integers and is strictly increasing before rotation. They strictly mentioned that the array contains unique integers and is strictly increasing before rotation. So example we have here is 3, 4, 5, 1, 2. 3, 4, 5, 1, 2. The example we have here is 3, 4, 5, 1, 2. Rotated version of basically 1, 2, 3, 4, 5. Here by looking at it we can say that this one rotated version, this one the array was 1, 2, 3, 4, 5, and the smallest number is 1. Right, the smallest number is 1. So we have to find the smallest numbers. Right, so we have to find the smallest number and we have to write the this one algorithm and big of logarithmic n time complexity. That's what they have given here. Right, so I hope this part is completely clear, easy. Right, so here also you can clearly see within this array 0 is the smallest element and we have to return 0, and within this one we have the smallest element that is 11, we have to return 11. So I hope the question is completely clear along with the examples. Right, so here let's discuss the approach first, followed by the edge cases, and then let's write the code. Right, so first thing that I want to tell you here is uh, we will be going with a binary search approach. We will be going with a binary search approach because the array is already sorted and it is rotated k times. Right, so binary search will be the best approach as we have to write the algorithm in big of logarithmic n time complexity. Right, so we'll be going with the binary search approach. Right, so let's consider the same first example, the first example that they have given in the question. 3, 4, 5, 1, 2. Right, so here let's initialize the low and right pointers. Here low to this one 0th index and high to for nothing but the last index, here fourth index or the last index. Right, so here nothing but the length of the array minus 1. So pure binary search. First we'll take 2 pointers, high and low and high. So we will initialize first this one to the lower index and this one high, the last index, high to last index. Right, so we will check if the array is already sorted. uh, yes, right, so we'll check if the array is already sorted. Nothing but in this case we'll check nums of low less than nums of high, nums of low less than nums of high, and we will return nums of low if it is true. If it is already sorted, and we have to return nums of low, right, if it is already sorted. So here, but it is the twist is it is rotated k times. Right, so now first what we will do, for that reason we'll be calculating mid first. First we'll be calculating the mid. So here this will be 0 low plus high by 2. Right, so this will be 0 plus 4 by 2, nothing but here in this case it will be 2. 4 by 2, it is nothing but 2. 2 mid will be 2 here in this case, and nums of 2 we have, nums of 2 is nothing but the index here 0, 1, 2. Nums of 2 we have 5. 5. Right, this we will compare with the nums of high. This we will compare with the nums of high. Nums of high is nothing but the last, this one, the element present at the last index. Nums of high, this one, fourth index. Right, currently it is at the fourth index, and this will be nums of high is 2. Right, so 5 is whether 5 is greater than this one 2. 5 is less than or greater than 2, will compare. Right, so 5 is greater than 2. So here in this case 5 is greater than 2. That is nothing but nums of mid is greater than nums of high here. If nums of mid is greater than nums of high, then the value is present at the right half. If the nums of mid is present at the, I mean, if suppose the value was 1, suppose I suppose the nums of mid we got was 1, and we are checking for with the nums of high, basically 1 2. 1 is greater than 2, no, less. If it is nums of less, this is just for the example sake, this we are not considering. I just wanted to show you if the nums of mid was less than this one, what do we call nums of mid is less, was less than nums of high, then we have to check the this one left. Then we have to go with the array of left. We have to check the left elements, the elements present at the left. So as nums of mid is higher than the nums of high here, I mean greater than the nums of high here, in this case we'll check the right part, we'll check the right part, right? So the min must be to the right. So we have to update low equals mid plus 1. Low equals mid plus 1 means 1. This one we are speaking now. We have the element 5 at the low. What are the elements that are present? Basically 1 and 2, right? So 1 comma 2 along with the mid. So now we have to calculate 1 comma 2. We are considering only right side, right? So we are considering only right part now. So now we will calculate the mid. Now we will calculate mid. So this will be 1 plus 2, 1 plus 2 by 2, nothing but 3 by 2. This will be 1. This will be 1. So nums of this one, nums of 1. So now we got nums of 1. So this is nothing but the 1. Now we have the element 1 comma 2. So uh, we have got the smallest element here. This one will be, will return this one, nums of 1. Nums of 1. After going with the left equals mid plus 1, we will return the smallest element. Now the mid element will be 1 comma 2. This will be 3 by 2 equals 1. Now what we'll do, we'll go with the nums of 1. We'll go with the nums of 1. See here, low equals 3, high equals 4. Low equals 3, high equals 4 means this one index they are speaking of, not the value. Low equals 3 and high equals 4 means here 0 1 2 3, third index is 1. This is what I showed, and high equals 4 means 2, right? So here low equals 3, high equals 4, and mid equals 3, because when we calculate mid, this will be 1 plus 2 by 2, nothing but 3 by 2 here on this case, right? So nums of 3 will be quite obviously 1. So here this one you can skip, or if you want to know this one, this is fine. Since nums of mid is less than or equal to nums of high, nums of mid is less than or equal to nums of high means here in this case 1 and 2 we have. So 1 is this one and this one is high. This one is high. Now mid is 1 and high is 2. So nums of mid is less than nums of high here, right? Nums of high. When nums of mid is less than nums of high, then we have to return nums of mid. Then we have to return nums of mid. The min is at the mid or left. So right, this one min is at the mid or to the left, right? So here when low equals high, when low equals high, we have to return nums of low, which is basically 1, right? So which is basically 1. Now we will consider only 1, right? We'll consider only 1. Now low is equal to high. So here this will consider as 1, right? So this is the element we'll be considering. Only left will go with searching only for 1 after this step. Basically after this step, the lowest number that we got is 1. Now low will be equal to high. Low, only one element we have. Low is also 1 and high is also 1. When low is high, we will return nums of low, nothing but it is 1. It is 1. So the output that we got here is 1, which is equivalent to the output that they have given for the example 1. So our approach works absolutely correct in this case. Our approach works absolutely correct in this case, right? I hope the approach part is completely clear. Complete this one, pure binary search, right? So here our approach works absolutely correct in this case. Let's quickly discuss the complexities. So as we have as they have mentioned in the question, we had to write the this one, what do we call the algorithm in big of logarithmic and time complexity. So we went with the binary search, right? So the time complexity is quite obviously big of logarithmic n here in this case, because we are performing the binary search by having the search phase. each time, right? So each time means first we went with complete numbers 3 4 5 1 2. So then we compared this one, 5 is greater than 2, 5 was greater than 2, so we went with the right half, right? So right half is nothing but 1 2. Next we considered 1 2, and then this one, within this one, this was small basically, right? So left was so basically nums of mid one was this one less than 2. This time nums of mid was less than nums of high, so we searched only one, we considered only one. Then we had only number here in this case. This one low was equal to high, we compared low was equal to high, as we had only number, so we returned low, we returned low. Here in this case we will return low. That is how we got the output basically, right? So here we are performing the binary search by having the search spaces every time we are having the search space and each time. So the time complexity would be quite obviously big of logarithmic n. What would be the space complexity here? Space complexity would be big of 1 here in this case. The space complexity would be big of 1 because we are making use of the constant space that is used regardless of its input time, that is used regardless of its input type. Here the space complexity would be big of 1 and the time complexity would be big of logarithmic n for the code that we'll be writing in the future, right? I hope the this one approach part is completely clear along with the complexities, right? So now as we are completely familiar with the approach and complexities, let's start writing the code. Initially let's make use of the low and high. Let's initialize the low to 0th index, and let's initialize the high to last index, nothing but here in this case nums dot length minus 1. Now let's go with the pure binary search here, nothing but low has to be less than or equal to high. Means here we have to continue until the search space reduces to one element, right? So this has to be not less than or equal to, this has to be low, has to be equal has to be less than high basically, right? Now there is a safe way to calculate the mid to avoid the overflow by calculating the uh, this one. We can just write it in this way: low plus this one will be high minus low by 2. This is fine. So the next step here would be there are only this one, what do we call, two conditions, right? So when nums of mid is greater than nums of this one high, low equals mid plus 1, we are going with a low equals mid plus 1. If nums of mid is less than nums of high, then we'll go with high equals mid, then we'll be going with a high equals mid. So here in this case let's write the simple if condition here: nums of mid, if it is greater than nums of high, here this one will be low equals mid plus 1. This is fine. Else what we will do? Else what we will do? High equals mid. High equals mid. This is fine. Let's come out of this one entirely. Finally, when low equals high, that's the minimum element. Nothing but here in this case, we will return nums of low. We will return nums of low. Right? So this is it for the code. This is it for the code. Let me hit the run button. So we articulated the same thing in the form of code that we discussed in the approach, right? So whatever the things that we discussed in the approach, the same thing we articulated in the form of code. So I hope this part is completely clear, right? Now the sample test cases are getting passed. So let me hit the submit button quickly. So here you can clearly see all the test cases are getting passed, means the code works absolutely correct in this case. I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.